This lecture is going to be an overview of cosmology, and then I'm going to segue into the question of life in the universe towards the end. So if you recall in this course, I started off this course by showing you this picture, which is a picture of the night sky. You're staring up at the Milky Way, an image taken from the southwestern United States. And you see up here this fuzzy band of light in the sky. And we know when we look up at the sky and we see this band, what we're really seeing is the integrated light from a huge disk of stars that we're embedded within. So if you're living on a frisbee, somewhere on that frisbee, and you're looking out to the sky, you're seeing the edge of that frisbee that lines up in the sky. You're looking through it. You're part of it. And all of the stars that you see over here and over here are part of that same frisbee, part of that same disk of stars that we live in. It's just that when you look out of the disk, you don't see the integrated light from all the stars along the plane of the disk, and you only see the stars that are sort of above you and the stars that are below you. But when you concentrate your look right along the edge of that disk that you're embedded within, all of the light piles up into this integrated band of light that we call the Milky Way. Now, of course, the sky that we look up and see looks very, very similar to the sky that our ancestors looked up to see. In fact, if you could look very closely on the walls of this canyon here, there are ancient petroglyphs carved into the walls. So you can imagine that those ancient people who carved those petroglyphs also looked up at the sky. And it's very unlikely that they understood that they lived in a big disk of stars that was 100,000 light years across. And that, in fact, there were many other disks of stars like that panning out into the universe. But it's probably true that they asked themselves some of the same questions that we are asking ourselves today. And in the field of scientific cosmology, we think we have answers to, actually. So this is the remarkable thing about scientific cosmology today, is that we have pretty good idea what the answers are to many of these questions that people have always asked. Like, how old is the universe? How many stars are there? What else is out there? Now, we don't know the precise answers to all these questions, but we have a reasonably good idea of a lot of things that's pretty remarkable if you consider the size and scope of the problem that we're confronting. And so we did a little bit of that in this class. So in this class, what I tried to do is not only tell you about what we think the universe is like, but at least give you some idea of why we believe it to be that way. So in this sense, just looking up at the sky and thinking about these questions, cosmology is the oldest science. So the oldest model of cosmology that, at least the longest lasting model of cosmology that we're aware of, is the old model of Aristotle and Ptolemy that had the Earth at the center of everything. And all the planets orbit around the Earth, and the sun orbits around the Earth. And there's this sphere of stars around us in the celestial sphere that's slowly turning around. Now, that's not necessarily a super crazy idea, because more or less that's kind of what things look like. And it took a long time for people to figure out that that's not actually what's going on. But eventually people did, and the reason why people did, and the reason why this picture eventually did change, is not because people weren't well, to some extent, but it wasn't really because people weren't imaginative enough to come up with other possibilities. In fact, there were people who lived a long time ago who came up with this idea that maybe the Earth goes around the sun. But there wasn't any hard evidence for it, and that also seemed too bizarre for a lot of people to accept. Now, eventually, people were able to make measurements to rule ideas, to test these ideas. And eventually, the measurements became so precise that they couldn't accept this idea anymore, that the Earth wasn't moving. and just sitting still and everything's going around us. In fact, observations like those that Galileo made with his telescope now, because he had a telescope, he could make precise observations that effectively ruled out this idea, this old model that Ptolemy had, and ushered in this new model where now the sun is at the center and all the planets go around the sun. And it was really the telescope that allowed this transformation to happen. It was basically the empirical method to go out and look at things and make measurements and find that, well, this model of Ptolemy's old model doesn't work anymore. And it's only Aristotle, it's only this picture that's similar to what Copernicus and Kepler were pushing that's consistent with the data. And what happened here was very transformative, not just because the Earth is suddenly not at the center of the universe anymore, but because the Earth is moving. And it's moving a pretty significant distance from one time of the year to the next. And the reason why this is so transformative is it implies that the stars are much, much farther away than anybody had previously thought was possible. The reason why this is because if the Earth is moving, and you look out at a distant star, you would expect to see the star move in its angular position on the sky from one time of the year to the next. And within the limits of what people could measure at the time, they could not see this. They couldn't see stars zigzag in the sky from one time of the year to the next. And the only way that this was possible is that for the stars to be very, very far away, to be much, much farther away than the distance between the Earth and the Sun. And so by accepting this model that the Earth is not at the center, that the Sun is at the center, it immediately implies that the universe is much, much bigger than anyone had previously imagined it to be. Now, interestingly, this story that happened in the 1400s, this Copernican revolution, another revolution like that happened later on. It turns out that with the Copernican revolution, we had to accept this idea that the universe was much, much bigger than all of the great imaginative thinkers had thought possible in the past. That happened again in the 20th century. In the 20th century, it was realized that not only were the stars really far away, and that we were embedded within a disk of stars, but this disk of stars was huge. It was very large, and moreover, there were many other disks of stars out there in the universe. So now we know that our galaxy, the Milky Way, is something like 100,000 light years across. Okay? And if the sun were the size of a small seed, if you took the sun, which is 100 times bigger than the Earth, and scrunched it down to the size of a small seed, then the edge of the galaxy would be at the moon. And I'm talking about the near edge of the galaxy would be at the moon. So we live in this galaxy that is immensely big, and moreover, around this time, not too long after this, in the early 20th century, Edwin Hubble would show that there were other galaxies in the universe, and that ours was just one among many island universes out there. And so again, the universe becomes bigger than anyone thought possible. Not only are the stars really far away, and the galaxies are really large, but there are many, many galaxies in the universe. And Hubble was able to do this because now, by the time Hubble was a scientist, there were telescopes that were so big, so much bigger than Galileo's telescope, that he could actually see individual stars sitting there in distant galaxies. Specifically, Andromeda was the one he was studying. He showed that this nebulous blur of light in the sky was actually composed of individual stars, meaning that it was a galaxy in its own right. Now, also around this time in the early 20th century, there was this guy named Albert Einstein who was working in a patent office. And he was thinking hard about the question of what is light. He was trying to understand how certain discoveries about the nature of electromagnetic radiation could jive with his general understanding of how physics should work. And he proposed this thing called the special theory of relativity, which was shown to be true based on large amounts of observation, that our perceptions of space and time are actually influenced by how fast we're moving. And working along with these ideas for the next 10 years or so, he eventually published a more general theory that's called the general theory of relativity that dealt with the concept of gravity. And in this theory, he showed that gravity, in fact, you could think of it as not a force that's tugging between objects the way Newton had thought gravity was, but in fact, gravity is something that is a consequence of massive objects warping space. So that space itself is no longer a fixed thing that's always been and always ever will be the same, but in fact is warping in response to massive objects. So if you put the sun here on this, what looks like a mattress, it makes a dip, and that curved space in response to this dip is what dictates the orbits of the planets going around the sun, for example. Now, one of the interesting consequences of this theory is that, like I said, space is no longer a static thing, and in fact, space can be dynamic. Space itself can change. And not too long after he published this theory, a guy named Friedman was studying Einstein's equations, and he realized that if you think about the entire universe in the context of Einstein's general theory of relativity, then it can give rise to a situation when the universe should be expanding. Now, Einstein saw this, and he said to himself, well, that's crazy. The universe should not be expanding. That's just too weird even for me. And so he decided to change his equations. And he added something like an anti-gravity term to his equations, which is now called the cosmological constant, to keep the universe from expanding. He would later say that this was his greatest blunder, the biggest mistake of his career, because not too long after that, in 1929, this same Edwin Hubble, who had access to this very big telescope, was studying galaxies. All these galaxies that he had shown were actually other galaxies in their own right, all these these nebulosities in the sky. And he found that when he measured the distance to these galaxies, and he plotted the distance to the galaxy as a function of the velocity of the galaxy, how fast it was moving away from us, he found that, first of all, it looked like all the galaxies were moving away from us. And the ones that were farther away were moving away faster. And it's this kind of behavior, this velocity versus distance function, is exactly what you expect in a universe that's expanding in the way that Friedman said Einstein's general theory of relativity should make it. So this, Hubble's observation that the universe is expanding, was arguably the first step along the road to modern scientific cosmology. This is some empirically based model of cosmology that asks the question, what is the universe as a whole doing? And how is it evolving? We're now under the realization that the fundamental constituents of the universe, the fundamental things that make up the universe on the grandest scales, are not stars, but in fact are galaxies themselves. And the universe you can think of as an assemblage of galaxies. And these galaxies align themselves in chains and filaments and clumps and clusters. And these galaxies dictate the large-scale motion, the large-scale structure of the universe. So by studying galaxies, the realization that galaxies were there and what they were provided this kind of opening insight into what the universe was as a whole and allowed people like Hubble to begin to study it globally. We had hand in hand a new theory for what gravity was and how the universe should behave in response to mass from Einstein. And those two things together just so happened to happen right around the same time. In the beginning of the 20th century, both of these things came together. Einstein's general relativity and telescopes that were large enough to actually make these observations. And together, these two things together allowed the theory of modern cosmology to begin. Now, eventually this idea that the universe is expanding led to a new model for what the universe was, how it began, and how it's going to proceed. And for lack of a better term, that's now called the Big Bang Theory. I think I probably mentioned this before, that the term Big Bang was originally supposed to be a divisive theory, a divisive word. So it was supposed to be sort of mocking this idea that the universe would begin with a Big Bang. But eventually, even proponents began to use it because it had a nice ring to it. The basic idea behind this theory is that the universe is expanding now, but if you run the clock backwards, it was smaller in the past. And if the universe is smaller in the past, it turns out that if you squeeze everything together, stuff gets hotter. So within this theory, the universe is smaller and hotter in the past, and as the universe expands, it cools. And so today, it's something like 14 billion years after the Big Bang, and the universe is very cold. But in the early universe, it was much hotter. So as you make the universe twice as small, it gets twice as hot. So if it's 3 degrees now, it was 6 degrees some time ago when it was half its size. Then it was 12 degrees, and then it was 24 degrees. And eventually, even though it seems cold, eventually it gets hot, it gets very hot. It's something like 300,000 years after the Big Bang, according to this theory. The universe is getting so hot that even light can't travel. So what's going on is the universe is so hot that atoms cannot hold on to their electrons. So electrons are flying around, and it turns out electrons are really good at scattering light. So if light tries to travel freely in the early universe, it scatters off these electrons. It can't, so it's very foggy. But as soon as the universe cools down to about, 3,000 degrees or so, the atoms can grab onto these electrons. The electrons go away, effectively, they get bound to the atoms, and light can shine through. So the universe becomes transparent, suddenly, all at once, right around 300,000 years after the Big Bang. And effectively, we should be able to observe this as a glow. There should be radiation left over from the Big Bang that we see from this time. In fact, in 1965, Penzias and Wilson discovered this glow left over from the Big Bang. And by studying this, they basically found some empirical confirmation that, in fact, the early universe was as hot as people were predicting it should be. So we have this observation that the universe is expanding, therefore likely smaller in the past. And we also have this observation that there's this glow, this radiation that's left over from some earlier time, which again is what's expected in this model, where in this theoretical picture, where the universe is hotter and smaller in the past, like you would get in this Big Bang model. It turns out there are a few other reasons why we think this Big Bang picture actually happened. I talked about these before, and I'm not going to go into too much detail with them now. But the first is the expansion of the universe that we've already talked about. The second is this cosmic microwave background that was discovered by Penzias and Wilson in 1965. The third is something I talked about in class that I'm not going to go into very much right now. That's called primordial nucleosynthesis. And what this is that because we know what the conditions should have been like in the very early universe, we know how hot it should have been, and we know what kind of matter should have been there at those temperatures, we can make predictions for the kind of light elements that should have been created in the hot Big Bang itself. So what kind of elements should emerge from this Big Bang in the absence of anything else? Turns out we predict that the universe should consist primarily of hydrogen and helium, and a little bit of lithium that's made in the Big Bang. And when we go out and we measure the fraction of matter that's in hydrogen, helium, and lithium, out in interstellar space where not much has happened with stars, we find that those abundances, the amount of hydrogen, helium, and lithium, is right on what you would predict in this model, this Big Bang picture. That's kind of indirect, I realize, but it's still pretty interesting because we have to know what the conditions of the universe were, it turns out, just 3 minutes after the Big Bang to get this calculation right. The final thing that we see is a little bit more empirical, a little bit more kind of intuitive, I think, and that's we actually see the universe changing as we look back in time. So what do I mean by that? So we can use the fact that light travels at a finite speed to look back in time. Okay? So I'm seeing all of you as you existed just a few milliseconds ago. Because it actually takes a finite amount of time for light from you to get to my eye. It doesn't take that much time, it doesn't really matter. But I see the sun as it was 8 minutes ago, because it takes light about 8 minutes to get to the sun, from the sun to here. And I see distant galaxies as they were millions of years ago. And the most distant galaxies, I see them as they were billions of years ago. Okay? So we see Andromeda about 2.5 million years ago, as it was 2.5 million years ago. That's the nearest big galaxy to us. But some of the most distant galaxies we can see, for example, with the Hubble Space Telescope, we're seeing them as they were more than 12 billion years ago. And that's a significant fraction of the time back to the Big Bang. And what we see when we look at this, we see that the universe is actually changing. As we look at things that are 5 billion, 10 billion, 12 billion light travel times away, we see that they tend to be different. Galaxies are more messed up looking in the past than they are locally. So we're really seeing evidence, direct evidence, that the universe is evolving, is not unchanging, in the way you might expect in a universe that wasn't expanding. It didn't have an actual birth time. It didn't actually form at some time in the past. Are there questions about this? Okay. So the final thing I want to talk about in this kind of review is, so I've sort of given you a little bit of a timeline of, we think the universe began at some point and it evolved. What makes up the universe? What is in the universe itself on the largest scales? And of course, what we see when we look out is we see galaxies. We see the stars that these galaxies have, and they're emitting the light, okay, like these things. We also see some gas and some dust sometimes. Like this picture from Hubble is showing these giant dust clouds that are illuminated by the light from background stars. But it turns out that we think that there's a lot of matter out there that you just cannot see. For example, if you look at a galaxy, and you could try to measure the mass of the galaxy by measuring how fast the stars in the galaxy are spinning around. This would be analogous to trying to figure out the mass of the sun by measuring how fast the planets are orbiting around the sun. You should be able to do this. And what you expect when you see a galaxy like this that has all the light in the middle and very little light in the outer part is you expect the stars to be whizzing around fast in the middle, and then as you get away from the center where all the stuff is, you expect their speeds to slow down. Just like Kepler's laws say they should. But it turns out that this is not what you see. Scientists like Vera Rubin in the 1960s were the first people to really measure these rotation curves of galaxies precisely. And what they were finding is that as you go out to the outer parts of galaxies, you see that the stars are going around just as fast in the outer parts as they are in the inner parts. And what this means is that there must be some kind of missing mass there, some additional mass that we can't see. And today we call that missing mass dark matter. It's dark because it doesn't shine. And it's matter because it attracts other things gravitationally. And that's about all we know about it. Most astronomers think that this dark matter is actually some form of as of yet, undiscovered elementary particle, something that's not on the periodic table. It's not a proton, a neutron, or electron. It's something entirely different. And that it's a hint that there's a rich structure to the universe that we just cannot detect in laboratories on Earth. That there's something else out there. And we're like icebergs floating on an immense sea of dark matter. The discovery of dark matter and the evidence for it really solidified in the 1970s. And that was weird enough, and astronomers have been dealing with it since that time. In the late 1990s, something even weirder than dark matter was discovered. And this stuff is called dark energy. So, astronomers in the 1990s were attempting to measure how fast the universe has been slowing down in its expansion. So what you expect is the universe is expanding. But because there's mass in the universe, all that mass wants to slow down the expansion. Much the same way if you had a ball and you threw the ball up in the air, the mass of the Earth would want to slow that ball down, and eventually it's going to come back down. Or if the Earth isn't massive enough, that ball will keep rising up forever, but it'll at least be slowing down on its way up. And so you expect trajectories for the expansion history of the universe, the typical separation between galaxies as a function of time, to follow a path where it was initially going very fast upward, began to slow down, and maybe turns back around. Maybe it rises up and slows down, but doesn't turn back around and just kind of travels forever, or something like that. And what astronomers were doing is they were trying to look back in time to see how fast the universe was expanding then. And again, the way you look back in time is you look at things that are very far away. So that's what they were doing. And what they found was something very weird. Okay? What they found is, rather than, if they looked back in the past, finding that the universe was expanding faster then, they found that it was expanding slower then. What that means is the universe is speeding up in its expansion. And that's the same kind of thing as if you take a ball and you throw it up, and rather than it slow down, at some point it speeds up and takes off like a rocket. Except there's no rocket. There's just the ball. So this kind of behavior is anti-gravity. And it turns out that this behavior, this kind of cosmological repulsion that you get, is exactly the same kind of phenomenon you would get if Einstein's cosmological constant, this thing that he added into his equations to fiddle with them, was actually there and just put on the other side of the equation. And right now, this idea of a cosmological constant is actually one of the best fits to the current data. So it could be that this stuff that's causing the universe to accelerate in its expansion is actually something, this cosmological constant idea that Einstein first proposed in the 1920s. Or just before that, I guess. Not quite the 1920s. More generally, we don't really know what is going on, why the universe is accelerating like this, and this behavior, this general stuff that we're talking about, is called dark energy. That doesn't mean we know what it is just because it has a name. So that's weird. And so what we have now is we have a pie chart of what the universe is made of. And it's a very embarrassing pie chart. Okay, because the whole thing is all the universe we know about, but this tiny sliver here, about 5% of the whole, is stuff that we understand. Okay? This 5% is basically made up of normal matter, stuff that we're familiar with, like neutrons and protons, and us. Everything else is some kind of dark stuff that we don't know what it is. 25% of the universe is in the form of this dark matter, and about 70% of the universe is in the form of this dark energy. So we know it's there, we can measure it, we can measure its presence, but we don't know what it is. Yeah?
Where do these percentages come from? 25% dark matter.
Right. Where do these percentages come from? That's the question. I didn't have a lot of time to go into all of the things that we use to determine these percentages. One of the ways in which you can determine these percentages is, in fact, by studying in great detail the cosmic microwave background, this glow that's left over from the Big Bang. It turns out that there are signatures in the cosmic microwave background that we can use to determine things like how much total matter there is in the universe, and what the total amount of dark matter and dark energy is when you add it all together. So that places one constraint. The other thing, there are other things we use to determine the other fractions of matter in the universe. For example, in dark matter or dark energy. One of them is just the expansion history of the universe itself that we've mapped out quite well. So, for example, the fact that the universe is accelerating in exactly the way it is allows us to place constraints on how much dark energy there is to a pretty good extent. And there are other things we can do to measure dark matter. So, for example, gravitational lensing, there are effects associated with gravitational lensing. I talked a little bit about that in this class that allow us to place constraints on how much matter there is here. Another thing that we can use actually is the clustering of galaxies in the universe. So the way galaxies cluster on the very largest scales is sensitive to how much dark matter there is, how much normal matter there is. And we can use the clustering of galaxies on large scales to also place constraints on these. So it turns out that there are probably 6 or 7 independent constraints on the quantities that go into this pie chart that have been used to come up with these numbers. These numbers are good to, when I say 25, it might be 22 to 27, sort of numbers like that. But within the last 10 years or so, we've actually figured out what this pie chart is. If this course were 10 years ago, I could not have given you this pie chart. So this is a fairly recent advancement in our understanding of things. But it's really at the level of a graduate course for graduate students to understand, pretty good, fairly precisely, how we get these numbers with great detail. But that's roughly how it's done. So, now we have this picture, which is pretty crazy if you think about it. So we have this picture where the universe began about 14 billion years ago, and this thing we call the Big Bang, which is just a name. And again, in this picture, it's cold now. It was hot in the beginning. In fact, it was so hot in the beginning that complicated stuff couldn't exist. Everything was broken down into its primordial products, its constituent particles, that we think are fundamentally underlying everything. As the universe cooled, eventually it was cold enough for light to travel freely. Before that time, it was so hot that it was basically foggy. Light could not travel. After about 300,000 years, the universe cooled down enough that light could travel freely. And when we see the light from this time. This is called the surface of last scattering. We see this light from the surface of last scattering today using our telescopes. We can study properties of this light to study what the early universe was like 300,000 years after the Big Bang. So from that point, the universe was about 3,000 degrees at this point. It continues to cool and cool. And eventually, all those atoms that I was talking about start to clump together. And eventually, they get dense enough to form the very first stars. And we think the first stars formed about 400 million years after the Big Bang. Eventually, those stars, enough of them got together to make galaxies. In these galaxies and around these stars, planets began to form. The first galaxy, our solar system formed about 9 billion years ago, 8 or 9. Our solar system formed about 4 or 5 billion years ago. And, of course, the sun emerged at about the same time. So somewhere in here, as the planets are forming, if we focus in on one specific galaxy, which is one among billions, but it's one we like a lot, the Milky Way, the Earth forms around a single star in that galaxy. And sometime after that, quite a long time after that, we have all these fairly intelligent people living on this planet, looking back and trying to figure all this mess out. Now, you might ask yourself, well, okay, that seems a little weird, because there's a billion stars, of order a billion stars in the galaxy, more than that. And there are billions of galaxies in the universe. And so on one planet, we have this intelligent life. So a lot of people look at this equation, they say, well, that seems unlikely, that there's only one planet that had life. And so people ask themselves, is there other life in the universe? And I think when most people talk about this, when they talk about other life, they're talking really about intelligent life. Now there's two ways of thinking about the question, is there other life in the universe? And I think either of them is fundamentally very interesting. So there's the question of, is there any kind of life at all? One cell, single cell life, bacteria, anything like that, anywhere else in the universe. And people are still looking, scientists are still looking even within the solar system. Is there evidence that there was past life on Mars, for example? We are quite certain that there's no intelligent life in the solar system except for us, depending on how you define intelligence. So that's kind of the first thing I thought I would address, because I think it's just the thing that people are most interested in generally. Now, the answer to this question is we have no idea, right? I mean, some of you may be convinced that we've been visited by extraterrestrials. I'm not. And so there's what we can basically do at this point is quantify our ignorance. But this is always an interesting exercise because it allows us to think a little bit about the quantities of interest. So there's this famous equation that was written down called the Drake equation that attempts to quantify the number of communicating civilizations there are within the galaxy. So these are civilizations, in principle, that have life that could possibly communicate with us in some way. So our peers, or maybe smarter than us, at least as smart as us, say. And this is the way you go about this. So the argument goes like this. The first thing you want to know is how many stars are there in the universe, in our galaxy, that are suitable for creating habitable planets. How many stars like that are formed every year in the galaxy? Okay. So the galaxy is constantly making stars, but of course stars are constantly dying too. And so what we want to know is how many new ones are made every year. And that number, it turns out we know that number pretty well. That number is somewhere between 5 and 20 every year. So let's just say 10. Let's say that every year there's 10 new stars born that, say, have conditions that in principle could have a planet around them. So how many of those stars actually make planets? I'll talk a little bit about what we think that answer is later. But let's say maybe 10%. Okay, so let's say maybe 10% of those stars make planets around them. And on what percentage of those habitable worlds does life actually arise? So let me be extremely bold here. And what I'm assuming here in making planets, what I'm talking about is planets that could host life. I'm sort of using that as a prerequisite. But let's just say that of those that in principle could have life, let's say every single one of them. Every single one of them makes some kind of life. I have no idea whether this is certainly an upper limit, right? It can't be less than 100%. So then the next one, number 4, is how many of those life-bearing worlds would give rise to intelligent life? So whatever processes make conditions such that if you start out with single-celled life, say, you eventually produce intelligent life. I have no idea whatsoever. I don't think anyone has an idea of this. Because we only have one example that we know of. Let's say 5%. I'm just making these numbers up. In principle, you can make your numbers up too, because I have the equation here. But I'm going to say 5%. Let's say 5% of those planets that can have life actually make intelligent life. Now, how many of those worlds with intelligent life develop technologies that release detectable signs of their existence into space? Okay. So this is another question that we don't know the answer to. Now, we have been releasing detectable signals into space since maybe the 1950s, depending on how you define detectable signals. When people really started watching a lot of TV, we started broadcasting all kinds of signals out into space. But, that's not the most efficient use of broadcasting signals. I mean, that's not the most efficient use of power, just broadcasting your TV signals in all directions to space. You might want to just have everything wired through Ethernet eventually. It's a lot more energy efficient. We might not be that loud for very long. Because once we get really smart and sophisticated, we probably won't just randomly shoot out I Love Lucy every way. Okay, we'll probably keep stuff more focused. So, it's it's unclear if the aliens, if they were monitoring us, would see Jersey Shore or not, and for how long, and whether we would really want that to be what they saw. So I'm going to say 50%. Like I just threw this out there. Let's say 50% of them actually launch signals into space. Another idea is just because you're intelligent doesn't mean you're going to build telescopes or radio telescopes or radio transmitters or anything like that. In principle, you could be very intelligent but just philosophical. You could be great meditators, You know what I mean? Like you could just be like great monks who, the society of monks who just kind of like, have this rich philosophical life and don't necessarily build spaceships and bombs and stuff, So who knows? Like this is just a huge unknown. I'm just trying to quantify how ignorant we are. Now, the last number is, how long do these civilizations last and produce these signals into space? How long are they actually launching these signals into space? So when Drake first wrote this down, I think what he was thinking is, well, at some point you blow yourself up, right? We're a little less concerned about that now, I guess. And what we're concerned about now is whether at some point you might use all the resources up on your planet or whatever. You know what I mean? How long is it sustainable to have super smart civilizations messing around on a planet? We don't know that either. We would like this number to be very large. But in principle, we know all of these numbers can't be that large. Because if they were all large numbers, we would have been visited by now. We'd have aliens parked in front of the White House. Okay, so they aren't all that big in principle. So if you add all these numbers up, it turns out you multiply all these numbers together. You can get a number. A final number, which is the number of communicating civilizations in the galaxy at any given time. And if I take all these numbers, which I thought were not that crazy, you can stick in your own numbers, the number I get is 50. So this says, according to my flawed and incorrect calculations, there are 50 communicating civilizations in the galaxy. So that's interesting. The problem is the galaxy is very big. The galaxy is 100,000 light years across. So if they were spread uniformly throughout, probably none of them have seen I Love Lucy yet. Right? So, but again, we don't know. We don't know the answer. I'll talk a little bit about our attempts to try to find the answer. Now, sometime before this, there have been some kind of interesting things that have been done to kind of, address this point from the scientific community a little bit. Sort of fun things that were done. So you probably remember the Voyager space, or maybe you don't remember. I'm sure you don't remember the Voyager spacecraft. Maybe you've heard of the Voyager spacecraft. These were two probes that sort of the most distant probes that have ever been launched. Currently, I think they'll maybe be overtaken sometime fairly soon, but they were launched out to survey the outer planets, and on them was this gold record. So it was a record. Tells you a little bit about like how arcane the technology must be to some ET who finds it. But on this gold record, there were these interesting things like recorded sounds, like a train whistle and a thunderstorm and a baby crying, and the words hello in multiple languages, classical music, stuff like that. And then these drawings that are supposed to somehow indicate to the aliens like where we are and what a transistor is and stuff like that. We're all impressed that we invented the transistor. Yes, right. Did I say that too? Yeah. Sorry. They won't know the difference. There's this other thing that maybe you've heard of too that's called SETI, the Search for Extraterrestrial Intelligence, which is this idea of monitoring nearby stars, very nearby stars with radio telescopes, and looking for signals that they don't appear natural. So you might expect, there are signals that in principle, if you were an alien civilization and you were targeting the sun, maybe you thought that the sun hosted a planet, you could send a signal that could clearly be differentiated from some random signal that a normal astronomical object would make. And this has been ongoing for some time. No signals yet. There's this thing called SETI at home, which is kind of fun that you can download, and your computer, during resting time, your computer can monitor these signals as well and look for some anomalous signal from a nearby star. So let's say SETI finds a signal. Okay, let's say it's looking at a nearby star and it sees a series of zeros and ones communicated from some alien civilization, and it says, please come visit. What do we do? Well, that's way above my pay grade. But let's just think about what it might take to visit such a place. So the nearest star to us, or the nearest bright star in the sky, Sirius, is 8.7 light years away. Now a rocket, a typical rocket, which travels at about 10 kilometers a second, which might seem pretty fast, would take 240,000 years to get there. So that's probably a no-go. Now, if you could somehow create a rocket ship that could travel at almost the speed of light, in principle, you could make something interesting happen. Okay, so traveling at almost the speed of light, 0.995 times the speed of light, a round trip would take a little less than 18 years. So, okay, that's getting there. But that's not so good because one of you would get in this rocket ship, go visit, have a great time, come back, then you'd be older than me, so you'd be basically dead. So you don't want that to happen. But fortunately, things would be a little bit better than that because there's time dilation. Remember how I talked about time dilation? If someone's traveling fast relative to you. So if you were a person doing the trip and you were traveling very fast, it would look to you like that planet was coming at you at a fast speed. And to you, it would appear to last only about 1.7 years. And so the round trip would be very short for you. So you could go and come back and still be nice and young. Of course, I would be extremely old by the time you got back because you would experience this time dilation. So you'd have to yell into my ear and explain to me what you saw. So in principle, if you had this technology, you could envision something like this happening. Now, the technical difficulty with this is that the practical problems of actually creating the amount of energy it would take to accelerate a rocket ship up to this speed is staggering. So we would basically need to develop something like fusion energy probably before we could ever envision doing anything like this. So I think that's why right now we're sort of saying, well, that's up to the aliens. They'll come see us because we'll assume that they have developed that technology. So what we would like to do then, so rather than just waiting for the aliens to come see us, we'd like to do something else. And in the meantime, scientists on Earth have been making some progress categorizing how many of these worlds there might be out there. This is the thing I want to end with today. It's talking about some recent advances in the discovery of what we call extrasolar planets. That's kind of a funny name. Extrasolar is supposed to mean they're not around the sun. But extrasolar really just means they're not inside the sun. So clearly all planets are extrasolar planets. But really extrasolar planet means in the jargon, planets that are just going around other stars besides the 8 that we know about around the Earth. Now, here's the galaxy. And we're not doing a great job searching all the stars in the galaxy because it turns out that you have to do very, very precise observations to find a planet going around another star. It's really, really hard business. And so far, we've only really searched about 300 light years around the sun. So here's the sun, and we've got all the rest of this galaxy to go. But, we start locally and move our way out. Now, the history of discovering planets around other stars has been really exciting in the last several years. There's really been an explosion in this field. What's plotted here is sort of a rate of discovery plot. So this is the date planets were discovered versus the number that were discovered going back in time. The first extrasolar planet was discovered in 1989. And for a long time, there were just a few. There were a bunch that were discovered in the mid-90s, but now the number of discoveries is going way up with time. So we now know that there are at least sort of 500 or so other planets. So there are other stars out there that actually have planets around them that we've detected. There's a great story that I heard from Jeff Marcy. Jeff Marcy is one of the arguably the most successful planet hunter alive. Now, he's one of the, he's not only just a great guy, but he's sort of, a great ambassador for astronomy. And he has discovered a number of these planets with a technique that he more or less pioneered along with a few other people. And he tells this great story that he was, back when he had this idea for how you might go about detecting other planets, the idea goes something like this. You've got a sun, okay? You've got a star right here. You've got a planet going around it. Well, according to Newton, there's an equal and opposite reaction. So this planet, the star tugs on the planet tugs on the star. And when the planet goes around the star actually has to respond to this. Like if you had a rope with an anvil on it and you were doing this, right? You've got to kind of adjust your weight to it as you go around. It's the same thing with that planet. So that big star is wobbling like this as the planet goes around. And why does this matter? The planet is crazy, crazy dim. Okay? It's very difficult to see the light from that planet. What you can see is the light from the star, and you can study that light really well. And so what they wanted to do was just look at that star and look for that wiggle, look for that jiggle with time. And it should wiggle in response to the orbit of the planet going around it. And depending on how massive the planet was, the more it would wiggle. Okay. This was his idea. And he sent proposals out to funding agencies, and he'd get these letters back that were like, that's crazy, you'll never see anything, we're not giving you any money. And so he's got these, like, at least at some point he had these things tacked up to his bulletin board on his wall, as he, sort of after he discovered all these planets. What you learn from this is you never believe an expert. Believe what you believe. So anyway, this technique was great. It ended up being very successful in discovering lots of planets. And so as time has gone on, techniques have gotten better, telescopes have gotten better, and that's why people have begun to discover more and more of these planets around other stars. The first planets that were discovered, it turns out, were pretty massive because it was easier to discover the massive planets because they jiggle their stars more. And so eventually more and more techniques were developed to discover extrasolar planets besides looking for this wobble. Now one of the questions that people are very excited about in this field is trying to figure out whether planets could be habitable. And the first order thing that most people think about when they're thinking about habitable planets is, could you have liquid water on the planet? So as far as we know, the existence of liquid water on Earth is fundamental to us having life. And so in the absence of anything else, any other information, we are assuming that if you have a planet around another star, that's at the exact distance to that star such that it could have liquid water, then we're going to call that a habitable planet. Certainly it wouldn't be habitable to us if it was much hotter or colder than that. And so you can see, for our solar system around a star like ours, the Earth sits right in the middle of the habitable zone, almost by definition. Mars is outside of it, and Venus is outside of it, but close. Okay? So, it turns out that finding these habitable planets, especially Earth-like, low-mass Earth-like habitable planets, is not an easy thing to do with the techniques that were first developed. So NASA launched a mission very, very recently that's just announced its first results called Kepler. Same Kepler who, we studied Kepler's laws earlier on, named after that Kepler. And the goal of this mission was to discover the frequency of Earth-like planets around other stars. So these are really the homes of ET. Can we find them? Well, not really ET, but at least Earth-like planets. And so this is what Kepler is doing. Kepler is looking basically out about 3,000 light years from the sun. Again, a very nearby region around the sun. And the method that Kepler uses is somewhat different. What Kepler is doing is, if it's looking at a star edge on, it's watching how bright that star appears to be, and it's waiting for a planet to go by. When a planet crosses in front of that star, it gets a little bit dim. Just a tiny, tiny bit dim, because that planet blocks the light. The bigger the planet is, the more of the light it blocks. And so if you watch how bright the star is, a little planet goes by, it does a little dip. A big planet goes by, it does a big dip, etc. So that's what Kepler's looking for. It's looking for just watching stars and watching them get a little bit dimmer and then brighter again. And that's watching the transit of this other planet going in front of it. So what it's basically doing is just monitoring lots and lots of stars and looking for them to dim and get bright again. So, so here's the field that Kepler is looking in. It's a certain field of space, and these three things right here were known planets. So those stars were known to host planets from other regions, from other studies in the past. And after 140 days of observation, so remember, all the previously known planets that we know about were discovered in the last 20 years, and there were about 500. In 140 days of observation in this single field alone, the stars that have candidates for planets are these. So what this is basically saying is the galaxy is filled with planets. And this idea that the existence of planets around other stars is rare is kind of gone now. We know because of Kepler that lots and lots of stars have planets. Moreover, the colors of the dots here reflect how big those planets are. So the blue ones are Earths. These are Earth-sized planets. And the big red ones are gigantic planets, like Jupiter or something. Now, it's harder to find the Earth-sized planets, but you see there's plenty of them out there already. And so these are just some of the planets that Kepler has discovered. This was just announced, like within the last month or so. Really big ones that are 16 times the size of the Earth, and little bitty ones that are about the same size as the Earth have been discovered around stars that, stars in our galaxy that are relatively nearby. 68 planets the size of the Earth have been discovered so far. These candidates, it's not, about 80% of these are going to be real, probably. They're going to do follow-up to confirm that they really are planets, but these are just rough numbers. And they've discovered a bunch of them that are Neptune-sized. They're just sort of everywhere. The other thing that Kepler did is they made this plot of roughly how hot the surface temperature of those planets should be. This is just a function of the size. The important thing is this band right here is the habitable zone. Stars that have temperatures that are about right to support liquid water. This is blown up. So all of these dots here are planets that Kepler has found, candidate planets that Kepler has found, that have temperatures that can support liquid water, at least close to liquid water. So just to calibrate you here, this is 100 degrees Fahrenheit. This is 50 degrees, and this is 0 degrees. So there are sort of a handful of planets there that have been discovered, 54 or so planets that have been discovered, again, in the last half a year, that are principle capable of having liquid water on them, which is pretty cool. So what does this mean? Well, I guess fundamentally it doesn't mean that much for your life, unless you're looking up at the sky. It's the same picture that I showed you before, and you look up. When you look up at the stars at night with your unaided eye, it's very, very clear. You can see about 2,500 stars with your eye. And what this means, what Kepler has found, is probably about 800 of them, or 850 or so, have a planet. And a good number of them probably have planets that have liquid water. Now, the other thing is, there's only 2,500 stars you can see, but the planet has about 70 billion stars. The galaxy has about 70 billion stars. And about a third of them, or maybe 300 million of them, well, a third of them probably have planets, and about 300 million of them have planets that can sustain liquid water on. And of course, keep in mind that there's a billion other galaxies just like ours. So odds are, there's other people looking back at us, but we don't know exactly how many. They probably don't, well, they may or may not know we're here. Probably haven't visited us, but it's still kind of fun to think about that. So this is the very, very end of the lecture. So what I thought I would do here is kind of give you a one-slide summary of what's been going on in the history of astronomy. So in 1917, the biggest telescope in the world was 100 inches in diameter. And this is a telescope that Edwin Hubble used to show that there were actually other galaxies besides ours. And he also used this telescope to show that the universe was expanding. Before this telescope was built, people did not have any idea that the universe should be expanding. It was totally unexpected. It was not built to look for that. But because that telescope was so big at the time, it was able to discover that. Flash forward to 1949, the biggest telescope in the world was the Palomar-Hale telescope. This was 200 inches in diameter. And it was this telescope that was used to discover the first quasars, the first objects in the universe that were in cosmological distances that light is coming from billions of years ago. So flash forward a little bit longer. And this was the Keck telescope, the largest telescope in the world currently today, optical telescope in the world, was built in 1993. Before this telescope was built, people had no idea that there would be this dark energy stuff that's propelling the universe to accelerate, and it was really because of Keck and observations supported by telescopes like Keck that we were able to discover this dark energy and now quantify it. So, of course, this isn't going to stop. There are plans within the next 5 years or so to build a 30-meter telescope, which will be this big. And, you know, we don't know what we're going to find, but it'll probably be cool. So that's it. Thanks a lot for the course, and we will see you